Hello there, and welcome to the Sleep Porch. Tonight, we drift into one of the most ancient and quietly powerful forces shaping our world: plate tectonics. This colossal force guides the rise of mountains, the birth of oceans, and the slow creation of continents on the planet we call home. It is the quiet pulse beneath every landscape you have ever known. A patient rhythm that reshapes Earth over millions, even billions of years. As you settle in, imagine the ground beneath you not as something fixed, but as a living surface, carried by vast rafts of stone that drift slowly atop deep, hidden currents far below our feet. We will explore wonders that lie beneath oceans, within mountains, and deep under the quiet skin of the planet. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, let your breath soften. Allow your body to grow heavy, and let the drifting world cradle your thoughts. Let's begin. The ground beneath you never stops moving. Even when the world around you feels calm and steady, the surface beneath your feet is always on a slow and silent journey. The outer shell of our planet is made of enormous slabs of solid rock that glide across a deeper layer that behaves almost like softened stone. This motion is far too slow for your senses to detect. Yet, over immense spans of time, it completely reshapes the surface of Earth. Mountains rise, oceans widen, valleys open, and continents drift to new places. Every familiar landscape owes its shape to this gentle, persistent motion. You can imagine the ground as part of a giant puzzle, but is always rearranging itself, guided by deep forces coming from the warm interior of the planet. Although we experience earthquakes and volcanic activity as sudden events, they are surface hints of a restless world always in motion. The quiet truth is that Earth never holds still, and the land, is already on its way to somewhere new. Earth's crust is split into giant, interlocking pieces. The outermost layer of our planet is not a single unbroken shell, but a mosaic of immense rocky sections that fit together like the surface of a cracked eggshell. These pieces are called plates, and each one spans enormous distances, carrying continents, oceans, or both. The boundaries between them are sites of constant change, where the plates meet, slide, separate, or dive beneath one another. Even though the crust feels unyielding and strong, it is thin compared to the layers below, and it drifts on top of a deeper zone that is much softer over long periods of time. These plates make sense of so many features around us, from deep ocean trenches to soaring mountains. Their motions determine where volcanoes appear, how coastlines evolve, and why earthquakes occur in certain regions. When you picture the entire planet covered with these colossal floating pieces, you begin to sense the graceful complexity of Earth as a living, shifting world. Tectonic plates drift at the speed of growing fingernails. The immense slabs that carry continents and oceans move at a pace so gentle it is almost poetic. On average, they drift only as quickly as your fingernails grow. This slow speed seems insignificant in everyday life, yet across millions of years, it changes everything. Entire oceans can open or close. Ranges of mountains can rise where none existed before. Islands can collide with continents or drift across vast stretches of open water. The reason we can measure this drifting so precisely is that scientists use sensitive positioning instruments anchored across the globe. watching the plates shift with exquisite accuracy. The slow movement hides a tremendous amount of energy, since these plates are incredibly massive. Their motion guides the history of life, the flow of water, the distribution of minerals, and the shape of every corner of the planet. Beneath the quiet of daily life, the Earth is always gliding forward in a slow, patient dance. Continents travel across the planet like slow rafts. The continents we know, with all their mountains, forests, deserts, and cities, are carried on the backs of plates that drift through time. Each continent behaves almost like a raft made of thicker and lighter rock that floats above the denser material of the mantle beneath. These continental blocks have wandered widely. Some once touched places they are now far from. Others join together to build supercontinents, only to drift apart again. The movement is steady rather than sudden. Yet over immense timescales, continents can occupy positions that drastically affect climate, ocean currents, and the unfolding of life. When a continent passes over a hot spot, it may spout chains of volcanoes. When two collide, the land can crumple upward into mountain ranges. Even quiet landscapes carry memories of these slow voyages. As you look at a world map, you can imagine every landmass slowly drifting, circling, and shifting as part of a vast and ancient journey. Mountains rise from plates colliding with immense force. When two plates press against one another, the pressure they generate can lift entire regions of rock skyward. Over millions of years, repeated compression folds and thickens the crust until great mountain ranges rise where flat plains once stood. This is how many of the tallest and most dramatic landscapes on Earth formed. The rocks inside these mountains often reveal astonishing histories, including traces of ancient oceans, deep buried roots, and minerals formed under crushing pressures. As mountains grow, they influence wind patterns, rainfall, and the movement of glaciers. They can even shape the evolution of plants and animals that live along their slopes. Although mountains feel eternal, they are always changing due to the uplift that builds them and the erosion that wears them down. What appears to be solid and timeless stone is actually a monument to the slow collision of plates, rising and reshaping the sky. Ocean floors are created at spreading ridges. Deep beneath the oceans are long underwater mountain chains where new crust is born. At these spreading ridges, molten material from the mantle rises upward through cracks created by the separation of plates. As this material cools, it forms fresh ocean floor that steadily moves away from the ridge in opposite directions. This process creates symmetrical patterns in the crust, including magnetic stripes that record the history of Earth's magnetic field. The ridges are dynamic places with volcanic activity that continually replenishes the seafloor. Hydrothermal vents flourish along these regions, hosting strange and beautiful ecosystems that thrive in heated water rich with minerals. Although the ridges are hidden beneath deep oceans, they are among the most active features on the planet. The creation of new ocean crust is part of a continuous cycle that shapes the seafloor and drives the slow expansion of ocean basins over geological time. The Pacific Plate is shrinking while others expand. Among the many plates covering Earth, the Pacific Plate is unique because it is gradually decreasing in size. This shrinking happens as it dives beneath surrounding plates along arcs of subduction zones. While the Pacific Plate diminishes, other plates grow as new crust forms along their spreading boundaries. This creates an intricate balance where Earth's surface area remains constant, even though individual plates change shape and size. The Pacific Plate plays a major role in global geology because its boundaries host intense volcanic and seismic activity. Many of the world's most active volcanoes sit along its edges. As the plate sinks deeper into the mantle, new geological features rise while older ones slowly fade away. This continual reshaping reminds us that Earth's plates are not fixed or silent. They are living parts of a restless planet, where creation and destruction are forever intertwined. Earthquakes trace the outlines of these hidden plates, revealing the quiet boundaries where the planet's deeper forces meet and shift. Although plates themselves are difficult to observe directly, their edges announce themselves through patterns of earthquakes. When plates shift, grind, or collide, stress builds along faults until the rocks suddenly slip. These slips send waves through the ground that scientists can record with sensitive instruments. By mapping where earthquakes occur, researchers can trace the outlines of known plates and even discover new or unexpected boundaries. These seismic maps often reveal structures far beneath the surface, including deep faults and zones where slabs are descending into the mantle. Earthquakes provide one of the clearest windows into the dynamic nature of our planet. Even though the events can be frightening, they also carry valuable information about how Earth works. Each tremor is a reminder that the ground is alive with continual motion, and that the planet's surface is shaped by forces operating on scales far larger than any one lifetime. The deepest trenches form where plates dive downward. In a few extraordinary places, the ocean floor plunges into narrow chasms that are deeper than any other locations on the planet. These trenches mark sites where one plate bends and sinks beneath another in a process known as subduction. The bending creates an arc of ocean floor that descends into the mantle, forming a long and shadowed depression. Life in these trenches persists under pressures so immense they would crush most organisms. The rocks here are transformed by heat, pressure, and the circulation of chemical-rich fluids. Above the trenches, arcs of volcanoes often rise on the overriding plate. These features highlight the power of descending slabs to melt material deep within the Earth. The trenches act as portals where crust is returned to the interior, continuing a cycle that has been operating for countless ages. They are among the most remote and mysterious environments on Earth, hiding worlds we have barely begun to explore. The Himalaya are still growing taller every year. The tallest mountain range on our planet is not finished rising. The collision between the landmass of India and the continent of Asia continues to push the ground upward as the two plates remain locked in a slow but powerful embrace. The rocks within the Himalaya bear witness to this immense force, showing signs of compression, folding, and uplift that reflect their ongoing rise. As the mountains grow, they influence regional climate by shaping monsoon patterns and capturing moisture carried by winds. Their glaciers feed major rivers that support millions of people. Although erosion carves valleys and wears down the peaks, the collision is strong enough to keep the range ascending over long stretches of time. Standing before these mountains, one can feel the weight of geological history still unfolding. The Himalaya are a living testament to the power of plate tectonics to sculpt the world. New oceans can split open inside continents. Across vast stretches of time, a continent can begin to stretch and thin until great cracks open through its interior. When this stretching becomes intense enough, the land slowly drops downward, forming long rift valleys that grow wider and deeper. Over millions of years, these rifts can fill with water and evolve into new ocean basins. This remarkable process shows that oceans do not only exist between continents, they can be born from the breaking of the continents themselves. As the crust pulls apart, magma rises into the gaps, solidifying into fresh rock and marking the earliest stages of a spreading ridge. What begins as subtle fractures can eventually become full ocean floors, with mid-ocean ridges, volcanic activity, and complex coastlines. Scientists study regions like the East African Rift to glimpse the birth of a future ocean. The idea that a sleeping continent can carry a young ocean within its seams reminds us that Earth is always changing, even in the places that appear most stable. Entire land masses can tear themselves apart. Continents may look permanent and immovable, yet deep forces can stretch and weaken them until they break into separate pieces. This tearing happens when mantle currents pull on the base of the crust, or when plates around a continent shift in ways that create tension. As the land stretches, it fractures into a patchwork of faults that slowly drift away from one another. Lakes may form along these faults as the land lowers, and volcanic activity can rise where the crust becomes thin enough for magma to reach the surface. In time, the stretching can widen so much that seawater floods in, creating a new coastline. This is how enormous regions that were once joined can end up thousands of miles apart. Geologists can trace the scars of ancient continental splits by studying matching rock layers and fossil evidence along distant shores. These separations reveal that continents are not rigid, but living landscapes shaped by deep forces acting over unimaginable spans of time. Subduction is nature's way of returning the crust to the mantle. One of Earth's most powerful processes unfolds where a tectonic plate begins its slow descent into the planet's deeper interior. This downward journey, known as subduction, draws surface rock into a realm of immense heat and pressure. As the slab sinks, it releases water and other materials it once carried from the ocean floor, setting deep geological forces quietly into motion. These materials help melt portions of the overlying mantle, generating magma that may rise to feed volcanoes. Meanwhile, the slab itself continues its journey into greater depths, gradually transforming into new kinds of rock as it encounters changing temperatures and pressures. Over millions of years, this recycled material becomes part of the mantle that drives plate motion from below. Without subduction, old crust would accumulate on the surface, and Earth would lose its ability to refresh and remake itself. The recycling of the crust is essential for maintaining a dynamic planet, and it is one of the driving engines behind the continuous evolution of our world. Volcano chains mark the tracks of moving plates. Scattered along the surface of Earth are remarkable lines of volcanoes that trace the slow migration of entire plates. These volcanic chains form when a plate moves over a stationary hotspot deep within the mantle. As the plate drifts, magma rises through the crust at different points along the plate's path, creating volcano after volcano in a long progression. Older volcanoes become extinct as they drift away from the hotspot, while new ones form above the rising plume. This process creates chains of islands or mountain peaks that record the direction and speed of plate motion. By studying these chains, scientists can reconstruct the history of a plate's journey across vast stretches of time. Some volcanoes in these chains rise from the seafloor to form entire island groups, while others create long, mountainous ridges on land. Each chain is a natural timeline, written in stone, showing how continents and oceans shift through the ages. The Ring of Fire is a global necklace of volcanoes. Encircling the Pacific Ocean is a sweeping arc of volcanic activity known as the Ring of Fire. This region contains the majority of Earth's active volcanoes, forming a vast chain shaped by the boundaries of the Pacific Plate. Along these edges, the plate dives beneath neighboring plates, producing intense heat and melting that fuel frequent eruptions. The Ring of Fire is also one of the most earthquake-prone areas on Earth, since subduction zones store and release enormous amounts of energy. The volcanoes here range from tall stratovolcanoes that dominate their landscapes to underwater peaks hidden beneath the waves. Many of these volcanoes have shaped human history, depositing fertile soils, forming islands, and sometimes unleashing powerful eruptions. The Ring of Fire is a vivid reminder that the edges of plates are among the most dynamic regions on the planet, constantly reshaped by forces rising from deep within Earth's interior. Hotspots create islands far from plate boundaries. Most volcanoes appear where plates collide or pull apart, but hotspots are extraordinary exceptions. These deep-rooted plumes of rising heat can punch through the crust in places far from any plate edge. When a hotspot reaches the surface, it feeds volcanoes that can build islands in the middle of oceans or erupt within continents far from tectonic boundaries. Hotspots are believed to tap into regions of the mantle heated enough to push melt upward toward the surface. Their eruptions can form chains of volcanoes that become natural markers of a plate's movement. Some hotspots remain active for tens of millions of years, building large volcanic plateaus or islands that drift away as the plate continues to move. The presence of islands in the middle of vast oceanic plates is one of the strongest clues that hotspots are deep and powerful features of Earth's interior. The Hawaiian Islands march across a fixed mantle plume. The Hawaiian archipelago is a clear illustration of how a plate can glide over a stationary source of rising heat. Beneath the Pacific Plate lies a plume that channels hot material upward, feeding volcanic activity at the surface. As the plate moves across this plume, new islands form directly above the hotspot, while older islands drift away and slowly erode. Each island in the chain represents a different moment in the plate's journey across the mantle plume. The youngest island sits above the hotspot and is volcanically active, while the islands further along the chain become progressively older and more worn. Deep beneath the ocean floor, extinct volcanic mountains continue the chain for a vast distance, extending the record far beyond the visible islands. This moving parade of land masses shows how the slow migration of a plate can create entire island chains that stretch across great reaches of the Pacific Ocean. Continental crust floats higher than oceanic crust. The continents rise above the oceans because the rock beneath them is made of lighter material that floats higher on the mantle than the denser rock beneath the seafloor. This difference in buoyancy means that continents stand tall, while ocean basins form deep depressions. Continental crust is thicker and composed of minerals rich in lighter elements, making it less dense than the dark volcanic rock that forms oceanic crust. Because of this, continents act like large floating platforms that resist being pushed downward. When plates collide, the lighter continental blocks often rise while the heavier oceanic plates sink. This contrast shapes the structure of Earth's surface and influences how the planet evolves. As continents drift, they carry their unique buoyancy with them, rising above the oceans like massive geological rafts. This natural flotation effect also helps preserve ancient crust, allowing continents to hold some of the oldest rocks on the planet. Plates carry ancient magnetism frozen into rocks. When molten rock cools at the surface or beneath the ocean, minerals within it lock into place and record the direction of Earth's magnetic field at that moment. These magnetic signatures remain locked within the rock even as entire plates drift across the planet. By studying these traces, scientists can pinpoint where the rocks first formed and how far they have journeyed since. This gives researchers the ability to reconstruct ancient continental positions with striking accuracy. The magnetic record is especially vivid on the ocean floor, where long bands of rock alternate in polarity-quiet evidence of Earth's magnetic field, flipping back and forth over vast stretches of time. These stripes form matching patterns on either side of spreading ridges, creating a detailed timeline of plate movement. The frozen magnetism within the crust is like a silent compass left by Earth's past, offering clues to how continents have wandered and how the planet's magnetic field has shifted through deep time. The continents have assembled and broken apart many times, long before the landscapes we know existed. The continents repeatedly gathered together into enormous supercontinents and then drifted apart again. This cycle is driven by the slow movement of plates that bring land masses together through collisions and later separate them as new oceans open. Each supercontinent forms a vast and unique world with its own climate patterns, ocean currents, and ecosystems. Over millions of years, heat builds under these giant land masses, eventually weakening their foundations and causing them to crack and split. The fragments then begin new journeys across the globe, sometimes joining other continents to form new supercontinents in future ages. Evidence of these ancient unions is found in matching rock formations, similar mountain ranges, and shared fossils across continents now separated by wide oceans. The continual assembly and breakup of supercontinents reveals that Earth's surface is ever-changing, shaped by cycles far larger and longer than human history can comprehend. Pangaea was only one of many supercontinents. Most people hear the name Pangaea and imagine it as the first and only time all the continents were joined. Yet the history of Earth stretches far deeper, and in that vast timeline, our world has assembled several enormous supercontinents that rose and fell long before Pangaea ever existed. Each one gathered almost all of Earth's land into a single colossal mass, forming ancient worlds with climates very different from today. Rivers flowed across endless interior plains. Coastlines were limited to distant edges. Winds carried moisture across thousands of miles of unbroken land. Before Pangaea came supercontinents such as Rodinia, Nuna, and others, whose names echo like distant memories in geological research. They formed, lasted for millions upon millions of years, and then slowly tore themselves apart as heat built beneath their foundations. Their fragments drifted across the globe and eventually collided again to create new supercontinents in later ages. When scientists reconstruct these ancient landscapes using rocks and minerals that preserve their original positions, it becomes clear that Earth's continents are participants in a recurring cycle of gathering and dryers. The world we know is only the latest chapter in a story told many times before. Earth may one day form a new supercontinent. The continents around us are still moving, and their journeys hint at a distant future where all land masses may once again come together to form a new supercontinent. The slow drift of plates is invisible on human timescales, yet it steadily reshapes the globe. Some researchers envision a future world where the Americas collide with Asia. Others imagine Africa drifting northward to close the Mediterranean and merge with Europe. There are even models that predict an entirely new supercontinent forming near the equator or closer to the northern regions of the planet. No one can say which path the continents will take, but all scenarios share one idea. The surface of Earth is not fixed. It is part of a long cycle, driven by heat within the mantle that pushes and pulls the continents in repeating patterns. A future supercontinent would alter climate, ocean circulation, and the entire layout of life on Earth. The quiet drifting we hardly notice today is already guiding the shape of the world that generations far beyond our own will inherit. This distant possibility reminds us that even the continents themselves are temporary forms in an ever-changing planet. The mid-Atlantic ridge pushes continents apart. Beneath the Atlantic Ocean lies a vast underwater mountain chain that snakes from the far south to the icy northern seas. This enormous ridge is a boundary where two plates are slowly moving away from each other. As they separate, molten material from deep inside the Earth rises into the gap and cools to form new ocean floor. This simple process, repeated continuously over immense spans of time, gradually widens the Atlantic Ocean. The continents on either side drift further apart as fresh crust pushes outward from the ridge. Scientists have mapped the ridge using sonar and have discovered that it is not a single smooth line, but a complex landscape of valleys, volcanic peaks, and fracture zones. The ridge is also home to hydrothermal vents, where superheated water, rich with minerals, bursts from the seafloor and nurtures unique life forms. All of this activity takes place in complete darkness, beneath miles of water. The Mid-Atlantic Ridge is one of the longest mountain systems on Earth, and it quietly reshapes the face of the planet with every passing moment. Iceland stands on a ridge that is splitting apart. Iceland is one of the few places on the planet where a major spreading ridge rises above sea level. The island straddles the boundary between the North American and Eurasian plates, which are pulling away from each other. You can stand in places where the Earth is literally pulling apart, where the ground cracks open, where valleys slowly widen with each passing year, and where fresh crust forms as molten rock rises from below. This unique geological setting is why Iceland is so intensely volcanic. The island rests directly on a place where the Earth opens itself, releasing heat and magma from deep within the mantle. The island's dramatic landscapes of lava fields, geysers, and steaming vents are reminders of the powerful forces shaping it. Iceland even grows ever so slightly larger as new material fills the space between the separating plates. It is a living laboratory of plate tectonics, offering a rare surface view of a process that usually happens far beneath the oceans. Africa is slowly tearing along the East African Rift. Deep within the African continent lies a spreading rift that is gradually pulling the land apart. The East African Rift extends for thousands of miles, marked by deep valleys, towering escarpments, and volcanoes that rise from regions where the crust is thinning. Lakes fill many of the low-lying areas created by this stretching, and some of these lakes are among the deepest on Earth. The rift is not a single fracture, but a network of faults and uplifted regions shaped by the complex forces pushing from below. Scientists believe that in the distant future, this rift may widen enough for ocean water to flood in, splitting eastern Africa into a new landmass. The rift is also home to some of the richest fossil sites on the planet, preserving evidence of early human ancestors who lived along its evolving landscapes. The slow tearing of Africa illustrates how continents change from within, transforming themselves through deep geological processes that operate far beyond the pace of modern life. The Red Sea is an infant ocean in the making. Between Africa and the Arabian Peninsula lies a long and narrow body of water that offers a glimpse into the early stages of ocean formation. The Red Sea sits above a spreading zone where the African and Arabian plates are pulling apart. As the land separates, magma rises to fill the gap, creating new crust that pushes the sides even further apart over time. This process mirrors the early development of major oceans, such as the Atlantic. The Red Sea is still young in geological terms, yet it already shows many features of a mature ocean. It has deep basins, active volcanic regions, and hydrothermal systems hidden along its floor. Over immense stretches of time, it will widen and eventually grow into a full-sized ocean with its own central ridge. Standing on its shores, you are quietly watching the birth of a future ocean basin. The Red Sea reveals that even today, the planet continues to create new oceans in real time. Australia is drifting northward toward Asia. The continent of Australia is not fixed in place. It is steadily moving northward, riding upon the Indo-Australian plate as it travels toward Asia. Modern positioning instruments placed across Australia measure this motion with remarkable precision, showing that the continent shifts a small but significant distance each year. Over millions of years, this slow drift will bring Australia into closer contact with the islands and land masses of Southeast Asia. Geological models predict that mountain building and changes in ocean circulation may follow as the two regions interact more directly. Australia's northward journey is part of a larger pattern of plate movements that shape the entire Pacific region. The continent's unique wildlife and ecosystems, which evolved in relative isolation, may encounter new environments in far-distant futures. The idea that a massive continent can slide across the surface of the planet without anyone noticing in daily life is a gentle reminder of how quietly Earth moves beneath us. California is sliding toward Alaska along a fault. Along the western edge of North America, a complex network of faults marks the boundary between the Pacific Plate and the North American Plate. The most famous of these is the San Andreas Fault, where the plates slide horizontally past each other. This movement carries parts of California slowly toward the region of Alaska over geological timescales. The sliding motion does not happen smoothly. Instead, tension builds along locked sections of the fault until it is released in sudden jolts that we experience as earthquakes. The landscape along the fault bears the marks of this ongoing motion. Streams are offset, valleys are twisted, and even mountains have been repositioned over time. Scientists carefully monitor these faults to understand how stress accumulates and how the land is shifting. Although the movement is measured in small increments each year, the cumulative effect is enormous. Entire regions are gradually migrating northward, guided by forces deep below the surface. Some plates have completely disappeared into the deep. The surface of Earth today is only a snapshot of a world in constant flux. Many plates that once shaped ancient oceans and continents have vanished entirely, carried downward into the mantle through long histories of subduction. Their remnants may linger far below, preserved as distorted slabs detected through seismic imaging. Some of these lost plates once formed major boundaries that influenced climate, ocean currents, and the distribution of life. Over time, as they sank deeper, they became part of the convecting mantle that fuels plate motion itself. Geologists piece together their stories using clues left in mountain belts, island arcs, and magnetic patterns preserved in rocks. These traces reveal where ancient oceans once lay and how continents approached or retreated from each other. The disappearance of entire plates reminds us that nothing on Earth's surface is ever truly permanent. Even immense structures of solid rock eventually return to the deep places from which they once rose. Off the western coast of the United States lies a small but important plate called the Juan de Fuca Plate. It is slowly slipping beneath the North American plate, in a region where the ocean floor is being drawn downward and returned to the mantle. This subduction zone fuels volcanic activity across the Cascade Range, a chain of volcanoes that includes peaks such as Mount Rainier and Mount St. Helens. As the plate descends, it carries water-rich oceanic crust into depths where heat and pressure release fluids that help generate magma. That magma then rises to feed eruptions at the surface. The plate itself becomes more compressed, heated, and altered as it moves deeper into the mantle. Over long periods of time, the Juan de Fuca Plate will disappear completely, leaving only its geological fingerprints behind. Its slow vanishing is part of the ongoing cycle that continually reshapes the margin of North America and renews the crust through subduction and volcanic activity. Ancient plate remnants lie buried deep in the mantle, far beneath the continents and oceans. Past layers of rock that shift over unimaginable spans of time lie the preserved remains of ancient tectonic plates that disappeared long ago. These slabs sank into the mantle through subduction and now rest as cold, dense regions suspended within the warmer, flowing rock around them. Scientists detect these ghostly relics by studying how seismic waves travel through the planet. The waves slow and speed up in patterns that reveal the shapes of hidden structures. Some of these buried slabs may be hundreds of miles long, folded and warped by the great pressures of the deep interior. They record the history of vanished oceans, forgotten boundaries, and long-lost land masses. Each sunken plate represents a chapter in Earth's past that ended millions of years ago when the surface changed and the old crust sank from view. The presence of these silent relics shows that nothing on the surface truly disappears. It simply returns to the depths, where it becomes part of the planet's long memory, waiting for scientists to uncover its story. The mantle flows like soft, solid rock over vast time. Deep beneath the crust is a realm that seems still and solid at first glance, yet behaves like a slowly shifting sea on geological timescales. The mantle is made of rock that is firm enough to feel rigid in the short term, but warm and pressured enough to flow very gradually over immense stretches of time. This flow moves so slowly that a single inch of displacement can take years. Yet the cumulative effect drives the motion of continents and the creation of mountains and oceans. Convection within the mantle circulates heat from the deep interior toward the surface, moving material upward and downward in cycles that last millions of years. The rock deforms in subtle ways, folding and stretching as currents push through it. This seemingly impossible mixture of solid strength and gentle fluidity creates the foundation for plate tectonics. When you imagine the mantle as a soft, ancient current furrowing beneath the crust, you begin to sense how Earth continually reshapes itself from within. Heat from Earth's interior drives plate motion. The immense motion of continents and oceans is ultimately powered by the warmth that radiates from the deep interior of the planet. This heat comes from the decay of radioactive elements, the lingering warmth from Earth's formation, and the slow release of energy trapped within the mantle and core. As heat rises through the layers, it creates convection currents that move material in great looping patterns. These slow movements push and pull the plates above, guiding the drift of entire continents. The flow is not forceful in a sudden way. Instead, it is persistent, patient, and constant. Over millions of years, the rising warm material and sinking cooler material create a hidden engine that shapes the surface of Earth. Without this deep internal heat, the crust would remain still, oceans would never open or close, and mountains would not rise. The landscapes we know owe their existence to energy that has been flowing from the heart of the planet since the earliest days of its history. Convection currents stir the mantle like a slow soup. Within the mantle, heat moves upward while cooler material sinks, creating enormous circulating currents that operate like a gentle churning motion. Although the mantle is solid rock, the pressures and temperatures allow it to deform slowly, permitting these currents to roll through it over millions of years. This movement drives the shifting of plates at the surface. Warm regions rise, spread out beneath the crust, and eventually cool enough to descend again, cycling continuously. These currents vary in speed and shape depending on the structure of the mantle and the thermal energy rising from below. They can lift parts of the crust, thin others, and create regions of tension or compression. These circulating flows are also responsible for hotspots and other deep plumes that generate volcanic activity far from plate boundaries. When scientists model these currents, they see a planet alive with slow, sweeping motion beneath a shell that appears solid from above. The mantle's internal stirring is one of the great engines of Earth's geology. Slab pull is one of the strongest forces moving plates. Among the many forces that influence plate motion, one of the most powerful is the downward tug exerted by subducting slabs. When a dense oceanic plate sinks into the mantle, its own weight acts like an anchor, pulling the rest of the plate behind it. This process accelerates the movement of the plate across the surface, guiding its direction and speed. The sinking slab drags cooler material downward and helps establish convection patterns that sustain the entire tectonic system. Slab pull can influence the formation of trenches, volcanic arcs, and the motion of continents connected to the plate. Scientists studying plate speeds often find that the fastest moving plates are those with large, subducting edges, proving how significant this force is. The strength of slab pull shows that gravity plays a powerful role in shaping the planet. As slabs descend, they help return old crust to the mantle and maintain the long-term recycling process that keeps Earth geologically active. Ridge push helps drive continents across the globe. At spreading ridges where new crust forms, the rising magma pushes the surrounding plates outward. As this hot material cools and becomes part of the ocean floor, it sits slightly higher than older, cooler crust further away from the ridge. This height difference creates a gentle slope that causes the newly formed crust to slide away, pushing the plates along with it. Although ridge push is not the strongest force affecting plate motion, it adds steady and significant pressure that helps move continents and oceans across the planet. This outward expansion is part of the balance between creation and destruction in plate tectonics. As new crust forms at ridges, older crust is consumed at subduction zones. Ridge push makes sure that the spreading centers continually supply momentum to keep the plates in motion. Over millions of years, this slow outward pressure can shift continents thousands of miles, altering coastlines, climate patterns, and the global layout of land and sea. The lithosphere floats on a layer called the asthenosphere. The outer shell of Earth, known as the lithosphere, consists of the crust and the uppermost portion of the mantle. It is rigid and strong, forming the plates that move across the planet. Beneath it lies the asthenosphere, a warmer and more flexible layer that behaves in a soft, deformable way over long periods of time. The lithosphere rests on this layer much like a raft on a slow-moving current. Although the asthenosphere is still solid rock, the heat and pressure allow it to flow slowly, enabling the lithosphere to glide above it. The boundaries between these layers influence how plates move, how earthquakes form, and how volcanic regions develop. The contrast between the rigid lithosphere and the softened asthenosphere is essential for plate tectonics to function. Without this underlying layer, the crust would be locked in place, unable to shift or reshape the planet's surface. The floating effect of the lithosphere creates the foundation for a dynamic and evolving Earth. The asthenosphere behaves like a warm plastic layer. The asthenosphere sits beneath the lithosphere and forms a zone of rock that is heated enough to become pliable over long spans of time. It is not molten, yet the combination of heat and pressure allows it to deform like warm plastic. This softening enables the plates resting above to move, bend, and interact with one another. The asthenosphere responds to stresses by flowing very slowly, redistributing material over millions of years. This behavior allows mountain ranges to rise, ocean basins to expand, and rifts to open as plates adjust to forces from below. The asthenosphere also transmits energy from deep convection currents that guide plate motion. Scientists study this region by observing seismic waves, which travel differently through the warm, pliable layer than through the cooler, more rigid lithosphere above it. The asthenosphere's rare ability to behave both as a solid and as a slow-moving fluid makes it one of the most essential layers within Earth. Deep inside the planet, Earth's interior holds more water than all of the oceans combined, hidden within minerals far below the surface. Deep inside the mantle, far beyond the reach of any ocean, is water locked within minerals in quantities that may exceed the combined volume of all the surface oceans. This water is not liquid in the traditional sense. It is bound within the crystal structures of minerals that form under intense pressure. As slabs of oceanic crust descend into the mantle, they carry water-rich rocks with them. The minerals transform under heat and pressure, storing water in ways that allow the deep interior to become a vast, hidden reservoir. Over time, this water can influence mantle melting, volcanic activity, and the buoyancy of rising plumes. When the mantle brings this water back toward the surface through volcanic processes, it contributes to the long-term cycling of water between the interior and the crust. The existence of this deep reservoir reveals that Earth's water story is far more complex than the oceans alone. The interior of the planet holds secrets that reshape our understanding of where water can exist in solid rock. Subducting plates carry water deep into the planet. When an oceanic plate sinks beneath another, it brings with it water that has seeped into cracks and minerals on the ocean floor. As the plate descends, this water becomes trapped within the rocks and carried into the high-pressure world of the mantle. The deep transport of water sets off processes that can profoundly affect the chemistry and behavior of the interior. At certain depths, minerals release some of this water, which helps melt the surrounding mantle and generate magma. This is one reason volcanic arcs form above subduction zones. Deeper still, other minerals capture water and store it within their structures, contributing to the hidden reservoirs deep inside Earth. This downward journey of water also softens rocks, influences how slabs bend, and helps maintain the long-term cycling of material between the surface and the deep interior. Subduction is more than the sinking of cold crust. It is a conveyor that carries water and minerals into the heart of the planet. That water helps create magma deep below volcanoes. When water is carried downward by a subducting plate, it does something extraordinary within the mantle. As the descending slab heats up, the water locked inside its minerals is slowly released into the surrounding rock. This water lowers the melting point of the mantle and allows it to partially melt at depths far greater than where ordinary surface water could ever reach. The resulting molten material begins to rise because it is lighter than the surrounding solid rock. As it travels upward, it collects in chambers where it evolves, mixes, and gathers enough pressure to feed volcanic activity at the surface. This deep-sourced, water-driven melting is responsible for many of the volcanoes that form along subduction zones. The presence of water also influences the chemistry of the magma, contributing to the explosive style of many eruptions in these regions. This process shows that the water cycle of Earth stretches far beyond oceans, clouds, and rain. Water moves silently through the depths and plays a vital role in the creation of new crust and the renewal of landscapes shaped by volcanic forces. Some volcanoes sit directly above subducted slabs. In many mountain belts and island arcs, chains of volcanoes rise in a nearly perfect line above the point where an oceanic plate bends downward beneath a continent or another oceanic plate. These volcanoes form because the sinking slab carries water and minerals deep into the mantle, where they help generate magma that ascends to the surface. The alignment between the descending slab and the overlying volcanoes is so consistent that geologists can trace the geometry of the slab simply by studying the location and chemistry of the volcanoes. In some regions, the slab is so steep that the volcanoes sit close to the trench. In others, the slab dips more gently, placing volcanoes farther inland. The depth at which the slab releases water can also influence the type of volcanic activity that occurs. These volcanoes often store vast reservoirs of magma that evolve over long periods of time before erupting. They are reminders that the surface of Earth is directly connected to the deep interior by pathways that channel heat, minerals, and molten rock upward from regions far beyond our everyday experience. Tremendous pressure transforms subducting rocks. As oceanic crust sinks beneath another plate, it enters zones of pressure so intense that the rocks begin to change their structure and composition. Minerals rearrange themselves into new forms that can withstand extreme conditions, creating rocks that only exist deep within the planet. Basalts from the ocean floor may transform into dense minerals such as eclegite, which plays an important role in pulling slabs downward because of its increased weight. Water trapped within the subducting crust can promote changes in mineral structure, further altering the rock. With continued descent, temperatures rise and the rocks undergo additional transformations, recording a journey that few samples ever survive. Occasionally, slices of these transformed rocks are thrust back to the surface through mountain-building processes. When they appear in exposed terrains, they become rare windows into the deep earth. These rocks reveal the intense pressures and temperatures that sculpt the interior of the planet. Their presence at the surface is a reminder that mountains can lift material from astonishing depths, transporting the stories of vanished slabs into daylight. Diamonds form under extreme plate boundary conditions. Diamonds may appear delicate and sparkling at the surface, yet their creation depends on brutal conditions deep within the mantle. They form where pressures are immense and temperatures are high enough to transform carbon atoms into rigid crystalline structures. Many diamonds originate at depths far below the crust, in regions where ancient slabs once descended, or where continents have thickened during collisions. The carbon that becomes a diamond may come from the mantle itself, or from material carried downward by subducting plates. Over time, volcanic eruptions known as kimberlite events transport these crystals to the surface at incredible speeds, preserving their structures before they can transform into ordinary carbon. The inclusions trapped inside diamonds can contain minerals that only form under extreme conditions, offering clues about the composition of deep earth. Some diamonds even contain tiny pockets of water or gases that reveal information about ancient mantle environments. Each diamond is a geological time capsule shaped by pressure, heat, and the long history of tectonic movement. The oldest ocean floor is surprisingly young. While the continents carry rocks that reach back billions of years, the story beneath the oceans is entirely different. Because new crust is continually created at spreading ridges and old crust is steadily pulled back into the mantle at subduction zones, the ocean floor is in a constant state of renewal, forever being remade by the planet's deep, patient rhythms. As a result, the oldest seafloor preserved today is only a small fraction of Earth's age. Older oceanic crust has long since been consumed into the mantle. This youthful nature of the seafloor helps scientists track plate movement, since magnetic patterns and rock ages preserved within it form a clear timeline of spreading and subduction. The relatively short lifespan of oceanic crust also reveals how efficiently Earth recycles its surface. While continents grow older and accumulate layers of history, the ocean floor undergoes a continuous cycle of birth and descent. Air. This rapid turnover is an essential part of plate tectonics, helping maintain a dynamic equilibrium between creation and destruction across the surface of the planet. Continents preserve billions of years of ancient crust. Unlike the ocean floor, continental crust is thick and buoyant, allowing it to survive far longer without being recycled into the mantle. This buoyancy protects ancient rocks that record some of the earliest chapters in Earth's history. Within continental interiors lie cratons, stable regions composed of extremely old rocks that have withstood countless tectonic events. These ancient fragments preserve minerals that formed when the planet was young, long before complex life appeared. By studying these rocks, scientists uncover evidence of early atmospheres, primitive ocean tectonic processes. The surfaces we walk upon often contain layers built over eons, recording volcanic eruptions, mountain-building events, and the collisions and separations of continents. These preserved histories allow us to trace the evolution of Earth from a young, hot world to the diverse planet we know today. The continents act as vast archives, holding memories that the oceans continually erase. Plate edges can flip and change direction. Plate boundaries are not fixed in their roles. Over the long spans of geological time, a region that once experienced spreading may later become a site of subduction. A margin that once pulled apart may later become a zone where plates collide. These flips occur when forces within the mantle shift, or when the geometry of plate interactions evolves. Evidence for these changes can be seen in regions where ancient spreading centers have been compressed into mountain belts, or where subduction zones have reversed direction. Sometimes the movement of one plate can drag another into a new configuration that alters the stress patterns of the entire region. These transitions show that plate boundaries are dynamic features, shaped by the deeper currents of the mantle. They evolve as the planet cools, as slabs sink, and as continents move across the globe. The changing nature of plate edges reveals how adaptable and interconnected Earth's tectonic system truly is. Plates sometimes break into new pieces. Although plates are massive, they are not indestructible. When stresses build within a plate due to mantle forces or collisions with other plates, the lithosphere can crack and split into new fragments. This process creates new plates or microplates, each with its own movement and boundaries. Such breaks can occur within continents or oceans and can lead to the formation of rifts, new spreading centers, or changes in the direction of plate motion. The splitting of a plate can influence volcanic activity, seismic hazards, and the long-term evolution of landscapes. Scientists detect these emerging fractures through patterns of earthquakes, GPS measurements, and the alignment of volcanic features. The creation of new plates shows that Earth's surface is still evolving. Even regions that seem stable can experience deep changes over geological timescales. The fragmentation of plates adds complexity to the global tectonic puzzle and demonstrates the planet's continual reshaping. Microplates hide between larger plates, like puzzles. Between the major tectonic plates lie smaller fragments, known as microplates. These pieces occupy narrow zones and often accommodate subtle shifts that larger plates cannot easily absorb. Microplates typically form where stresses create complex patterns of faults and fractures, such as near spreading centers, transform boundaries, or regions where several plates converge. Although small compared to continental plates, microplates play an important role in the overall behavior of Earth's surface. They can move at different speeds and directions, sometimes rotating or sliding between their larger neighbors. Scientists study these microplates to understand how stresses are distributed across plate boundaries and why certain regions experience frequent earthquakes. The presence of microplates reveals that Earth's lithosphere is not simply divided into a few large pieces. It is a detailed, intricate mosaic with many smaller components that fit together like a vast geological puzzle. The Caribbean Plate is a tiny, independent traveler. The Caribbean Plate is one of the smaller but more geologically active plates on Earth. Nestled between the North American, South American, Cocos, and Nazca plates, it moves independently through a region filled with subduction zones, volcanic arcs, and transform faults. Its motion creates a chain of islands that curve across the Caribbean Sea, many of which host active volcanoes fueled by the subduction of the ocean floor beneath the plate. The Caribbean Plate also carries deep basins, underwater plateaus, and ancient crustal fragments that hint at a long and complex history. Its boundaries are sites of frequent earthquakes as it interacts with the larger plates surrounding it. The independent movement of this small plate demonstrates that even modest-sized fragments of the lithosphere play significant roles in shaping regional landscapes and hazards. The Caribbean region owes much of its beauty and complexity to the steady motion of this tiny traveler. The Nazca Plate creates the Andes as it subducts. Along the western edge of South America, one of the most dramatic geological processes on Earth unfolds as the Nazca Plate sinks beneath the continent. This subduction generates immense pressure that folds and uplifts the crust, giving rise to the towering Andes. As the oceanic plate sinks downward, it carries water-rich minerals into the deep mantle, where they help create magma that rises to fuel the volcanoes along the mountain chain. The meeting of the descending slab and the overriding continent forms a region of powerful earthquakes and continual transformation. Stretching for thousands of miles, The Andes rise in sweeping grandeur, home to some of the tallest peaks on Earth outside the Himalayas. Their rocks preserve a long history of collisions, volcanic eruptions, and crustal thickening. The ongoing motion of the Nazca Plate ensures that the Andes continue to evolve, slowly rising, shifting, and transforming as one plate dives beneath another. This endless interplay demonstrates how deeply interconnected the surface of Earth is with the great forces hidden below. The Mariana Trench marks Earth's deepest descent. In the western Pacific Ocean lies a feature so deep and shadowed that it feels almost like a boundary between worlds. The Mariana Trench marks the point where the Pacific Plate bends downward beneath the Philippine Sea Plate, creating the deepest known place on Earth's surface. The trench plunges more than 6 miles below sea level, forming a narrow arc of darkness where pressure is immense and sunlight never reaches. Life endures even here, in forms adapted to the crushing environment, feeding on nutrients that drift down from above or rise from chemical reactions along the seafloor. The trench is part of a larger subduction system that fuels volcanic arcs, deep earthquakes, and long chains of underwater mountains. The shape of the trench reveals the angle of the descending slab and offers clues about how oceanic crust ages, bends, and eventually sinks into the mantle. The Mariana Trench stands as a reminder that the surface of Earth hides vast realms still largely unexplored. Tsunamis begin when seafloors suddenly shift. Tsunamis are often imagined as enormous walls of water, yet their origins lie in subtle and unseen movements far below the ocean's surface. Along subduction zones, stress can build as plates press together until the seafloor abruptly slips. When this locked portion of the plate finally gives way, it lifts or drops large sections of the ocean bottom in a single moment. The displacement pushes huge volumes of water upward, creating long waves that spread across the ocean at incredible speeds. In deep water, these waves are barely noticeable, yet as they approach shallow coastlines, they rise into towering surges capable of reshaping entire landscapes. Volcanic eruptions, landslides, and even meteor impacts can also trigger tsunamis. But the sudden shifting of seafloors is one of the most common causes. Scientists monitor subduction zones and use seismic and ocean sensors to detect these events as quickly as possible. Tsunamis demonstrate how tightly the surface of the ocean is linked to the hidden motion of the plates beneath it. Island arcs form beautiful curving chains across oceans. When one oceanic plate sinks beneath another, a graceful arc of volcanic islands often forms above the point where the descending slab releases water into the mantle. This water promotes melting that generates magma, which rises to build volcanoes at the surface. Over long periods of time, these volcanoes can grow tall enough to break through the ocean and form island chains that bend in sweeping curves. The shape of these arcs reflects the geometry of the subducting plate, which bends into the mantle like a great ribbon. Island arcs, such as those found in the Pacific, are home to lush forests, active volcanoes, and deep ocean trenches that trace the outline of the sinking slab. Their curved form tells a story of motion, pressure, and the deep processes that continually shape the ocean floor. These arcs are dynamic landscapes where earthquakes, eruptions, and island building occur side by side as part of a single, interconnected system. Volcanic arcs can grow into massive mountain ranges. Volcanic arcs begin in the ocean, where subduction generates magma that builds volcanoes along a curved line. As time passes and continents drift, these arcs may collide with larger land masses. When this happens, the volcanic islands become welded onto the edge of the continent, adding layers of new crust that can eventually uplift into extensive mountain belts. Some of the world's most impressive mountain ranges contain the remnants of ancient volcanic arcs that were long ago sutured to continental margins. These collisions add material to the crust, thicken it, and drive further uplift. The process can also trigger new episodes of melting, feeding, additional volcanic activity that contributes to the growing landscape. Over millions of years, erosional forces shape these mountains into rugged peaks and deep valleys. The origin of such ranges is often recorded in the chemistry of their rocks, which bear the unmistakable signatures of volcanic arcs raised from the sea and transformed into towering landforms. Some continents contain the ghosts of ancient arcs. Hidden within the bedrock of many continents are fragments of volcanic arcs that formed long before humans existed. These arcs once stood as island chains above subducting plates, but over millions of years they drifted toward continents and became fused into their margins. Geologists discover these ghosts by finding rocks with chemical fingerprints that match volcanic arc origins. Some consist of volcanic flows, ash layers, and intrusive bodies that cooled within ancient island settings. Others include deep-sea sediments that were trapped and uplifted as the arc collided with a continent. These preserved fragments provide clues to the history of vanished oceans and the long journeys of plates. They reveal when continents grew through accretion, when they collided with neighboring land masses, and how mountain belts were assembled. The presence of these ancient arcs shows that continents are patchworks made from many earlier worlds stitched together across deep time. The Himalaya hide rocks that once sat on ocean floors. It may seem impossible when standing before their vast, snowy peaks, but some rocks in the Himalaya were once part of ancient ocean basins. When India drifted northward and collided with Asia, the ocean floor between them became trapped and forced upward during the immense compression of the collision. These rocks were folded, crushed, and lifted to altitudes far above sea level. Today they appear as sequences of marine sediments, basaltic crust, and fragments of deep ocean minerals embedded within the highest mountains on Earth. Their presence proves that the Himalaya are the result of a monumental convergence between continents. As the land pushed upward, the once flat layers bent and folded into intricate patterns, preserving the story of the collision's force and endurance. These uplifted oceanic rocks offer rare traces of ancient seas that disappeared when drifting land masses met and reshaped the entire region. From the remnants of a closing ancient ocean, the Alps slowly rose into the dramatic mountains we know today. Long before the Alps towered over Europe, an ancient ocean lay between the plates that would eventually form this famous mountain range. Over millions of years, the ocean narrowed as the African plate moved northward, pushing sediments and crust toward the European continent. Eventually, the ocean closed entirely, as Africa continued its slow approach. The pressure of this collision forced the seabed upward, folding its sediments into the rising Alps. The rocks within the range record this story in layers of limestone, shale, and metamorphic minerals that were once buried beneath deep sea ether. As the collision continued, the crust thickened and mountains grew ever higher. Glaciers later carved the dramatic valleys that now define the landscape. The Alps stand as a testament to the closing of an ancient sea and the immense power of plates converging in a long and patient embrace. Greenland may have been connected to Europe long ago. The island of Greenland, now separated from Europe by the cold waters of the North Atlantic, once lay much closer to the continent and may have been directly connected to parts of what is now Scandinavia. Geological evidence on both sides reveals matching rock formations and ancient mountain belts that suggest these regions shared a common origin before the Atlantic Ocean began to open. When spreading started at the mid-Atlantic ridge, Greenland was carried westward on the North American plate, while Europe drifted eastward on the Eurasian plate. This slow separation widened the ocean between them and isolated Greenland in its current position. Scientists continue to study magnetic patterns, fossil distributions, and rock ages to refine the ancient connection between Greenland and Europe. The history preserved in these rocks reminds us that coastlines and continents shift through time, rearranging themselves in ways that are unrecognizable compared to modern maps. Antarctica once had forests and dinosaurs. The frozen continent of Antarctica, now covered with thick ice and buffeted by relentless winds, once hosted lush forests and thriving ecosystems. Before it drifted to the southernmost part of the globe, Antarctica occupied warmer latitudes, where its climate supported trees, flowering plants, and even dinosaurs. Fossilized leaves, petrified wood, and ancient bones have been discovered across the continent, revealing a world utterly different from the icy expanse that exists today. As Antarctica moved southward on its plate, ocean currents and atmospheric patterns shifted, gradually cooling the region. Over countless millennia, glaciers advanced, and the continent transformed into the frozen landmass we know. The ancient forests and animals vanished, leaving only their geological remains. These fossils show that plate motion can drastically alter the fate of entire continents, transforming vibrant landscapes into remote, icy deserts through slow and inexorable movement. The Atlantic Ocean was once closed like the Mediterranean. The wide Atlantic Ocean, which now separates continents and shapes global weather patterns, began as a much narrower and more confined space. Long before its deep waters existed, the area that would one day become the Atlantic resembled something far closer to the present-day Mediterranean. It was bordered by land on many sides and filled with young, shallow seas resting between slowly stretching continental plates. Over millions of years, tension built as the land masses on either side drifted apart. Faults opened, molten material rose, and the first hints of an oceanic basin began to appear. As spreading continued, the narrow seaway widened until an entire ocean unfurled across the planet. The transformation from a closed sea to a vast ocean altered climates, guided the evolution of countless species, and reshaped global circulation. Modern coastlines still hold quiet clues to this ancient transformation, reflected in matching rock layers and mirror-like continental shapes. The Atlantic reminds us that even the vastest oceans begin as small rifts, slowly widening over the ages. The Mediterranean, meanwhile, is the lingering remnant of a much older ocean. Today it appears as a beautiful enclosed sea, framed by continents and steep, rugged shores. Yet beneath its surface lies the memory of a world that once looked very different. Yet it holds the last surviving waters of an ancient ocean, known as Tethys. This older ocean once stretched across much of the globe, separating huge landmasses before the rise of modern continents. As Africa moved northward and collided with Europe and Asia, the mighty Tethys Ocean slowly closed, leaving behind only small remnants of its once sweeping expanse. The Mediterranean is the most significant remnant of this vanished world. Beneath its waters lie fragments of ancient ocean crust, folded sediments, and mountain roots that formed as the surrounding plates collided. At times in its history, the Mediterranean nearly dried out when its connection to the Atlantic was cut off, filling with thick layers of salt that remain buried beneath the seafloor. Every coastline around it carries clues of the long transformation from a global ocean to an enclosed sea. The Mediterranean stands as a window into a past world that shaped the very layout of modern continents. Plate motion has changed Earth's climate over time. The movement of continents has influenced Earth's climate more profoundly than almost any other natural force. As plates drift across the globe, they redirect the paths of winds and ocean currents, which in turn alter global temperatures and precipitation patterns. When continents cluster together near the equator, they can trap heat and create warm, humid climates. When they drift toward the poles, they can foster cold conditions and encourage the formation of ice sheets. The opening or closing of oceans changes how warm waters circulate, sometimes cooling whole regions or warming others. Mountain-building events caused by collisions can also reshape climate by redirecting airflow and affecting how moisture travels across the landscape. Over millions of years, these shifting arrangements have helped trigger ice ages, warm periods, and dramatic swings in global conditions. The slow motion of the plates creates a constantly evolving planet where climate is never truly fixed, but always responding to the shifting shape of Earth's surface. Continental positions affect global ice ages. Earth's history is marked by long cycles of glaciation, and the arrangement of continents plays a major role in determining when ice ages begin. When large land masses drift toward the poles, they provide stable surfaces where snow can accumulate year after year. Over time, this snow compresses into ice sheets that grow thicker and spread outward. The presence of ice reflects sunlight, cooling the planet even further and reinforcing the glacial cycle. If continents cluster in certain patterns, they may also disrupt ocean currents that normally carry warm water to higher latitudes. Without this warmth, polar regions cool dramatically, and ice can advance across vast areas. Geological evidence shows that at different times in the past, continents sat in positions that encouraged global cooling and allowed ice sheets to expand across multiple regions. These slow continental journeys reveal that climate is shaped not only by the atmosphere, but by the shifting geography beneath it. Ocean currents shift when continents move. The oceans circulate through a complex network of currents that transport heat, nutrients, and life across the globe. The shape and position of the continents determine how these currents flow. When the continent drifts into a new position, it can block old pathways and open new ones, radically changing how water moves. The creation of the Drake Passage near Antarctica, for example, allowed a powerful circumpolar current to form, isolating the continent and contributing to its deep freeze. The opening of the Atlantic altered the flow of warm water from equatorial regions, helping shape the climate of Western Europe. As continents separate or collide, narrow seaways can widen into oceans or close entirely, diverting currents into new patterns. These adjustments influence global climate, marine ecosystems, and weather systems. Every shift in ocean circulation is a reminder that plate tectonics guides the heartbeat of the oceans. Some continents once sat near the South Pole. The continents we know today have not always occupied their familiar positions. At various times in Earth's history, several large land masses wandered into cool southern latitudes, where they spent long periods near the South Pole. Evidence for this polar past comes from glacial deposits, striated rocks carved by ancient ice sheets, and fossils of cold-adapted plants that once grew near the edges of massive glaciers. In some cases, entire continents carried these glacial scars, before drifting back toward warmer climates. The shifting of continents through polar regions helped trigger large-scale climatic events, including periods when ice covered much of the planet. These journeys reveal that even the warmest regions known today may once have been frozen landscapes. The wandering paths of continents across latitude lines transform climates on global levels and help explain the dramatic climatic shifts preserved in the rock record. Plate tectonics shapes where animals and plants evolve. The drifting of continents has created new environments, isolated populations, and opened pathways that guided the evolution of life. When the continent splits, species are separated and begin evolving independently, often resulting in entirely new forms. When continents collide, land bridges can form, allowing species to migrate into new territories and compete with existing ecosystems. Mountain building events create fresh habitats with varying temperatures and elevations, encouraging species to adapt in creative ways. The movement of plates also influences climate, which in turn affects where plants and animals can thrive. Over millions of years, these changes have shaped the distribution of life across the globe. Many unique species found on isolated continents owe their origins to long periods of separation caused by plate motion. Plate tectonics is not just a physical process. It is one of the great architects of Earth's biodiversity, quietly shaping how life rises, spreads, and transforms across the planet. Fossils preserve the memory of ancient connections between continents. Long before plate tectonics was understood, scientists noticed remarkable similarities in fossils found on lands now divided by vast oceans. Identical species of ancient plants and animals appeared in far-separated regions, offering early clues that these continents were once joined long ago. Fossils of the reptile Mesaurus appear in both South America and Southern Africa. Yet this creature could not have swam across an entire ocean. Fossilized plants from the coal-forming forests of long ago appear on continents now far apart. These puzzles created early clues that continents had drifted through time. Today, these fossil patterns help reconstruct ancient supercontinents, showing where land masses once joined into larger forms. Fossils provide a biological map of Earth's past geography, confirming that life once moved freely across regions now separated by oceans. They reveal a world far different from our own, shaped by long-vanished connections. South America and Africa share matching geological clues. The eastern edge of South America and the western edge of Africa fit together like two pieces of an ancient puzzle. Beneath their shorelines, matching rock formations, mineral deposits, and mountain structures reveal that these continents were once joined. Identical layers of sandstone, volcanic rock, and ancient sediment appear on both sides of the Atlantic. Fossils preserved in these rocks show that the same plants and animals once lived across a single, connected landmass. When the Atlantic began to open, the rift tore this shared landscape apart, leaving mirrored geological features on opposite continents. Today, scientists still use these clues to trace the opening of the ocean and the spreading of the mid-Atlantic ridge. The geological match between South America and Africa is one of the strongest lines of evidence that continents drift, reshaping the world across immense stretches of time. India raced northward faster than any other continent. Among all the continents that have moved across Earth, India holds a remarkable distinction. After breaking away from the ancient supercontinent Gondwana, India began a rapid journey northward across the Indian Ocean. Paleomagnetic measurements revealed that it traveled at a pace far faster than typical plate motion, driven by powerful forces acting on the plate beneath it. India's speedy voyage eventually led to its collision with Asia. An impact so forceful that it built the Himalaya and uplifted the Tibetan plateau. The rocks in the collision zone preserved the staggering compression created by India's arrival. This journey altered global climate, changed ocean circulation, and reshaped the geography of an entire region. India's fast-moving past shows how even enormous land masses can behave unpredictably under the influence of deep mantle forces. It remains one of the most dramatic examples of continental motion in Earth's history. The collision of India and Asia changed the entire planet. When India reached the southern edge of Asia after its unusually rapid journey, the impact reshaped not only the region, but the entire planet. The force of this continental collision caused the crust to crumple, fold, and rise into the Himalaya, which became one of the tallest mountain ranges on Earth. As India continued to push beneath Asia, the Tibetan plateau rose and expanded, creating a vast, elevated landscape that influences weather patterns across half the globe. The collision altered atmospheric circulation by redirecting jet streams and strengthening seasonal wind systems. It changed ocean currents, affected the delivery of moisture, and helped shape the monsoon cycle that supports billions of people. The uplifted terrain also exposed deep rocks to erosion, drawing carbon dioxide from the atmosphere as these rocks weathered, which in turn cooled the planet over long periods of time. This single continental collision demonstrates how the motion of a plate can influence climate, ecosystems, and the global balance of life for millions of years. The Himalaya influence monsoons and global winds. The Himalaya do far more than rise majestically above the landscape. Their immense height and width act as a barrier that shapes the movements of winds and moisture across Asia. When warm, moisture-rich air flows northward from the Indian Ocean, it encounters the towering wall of mountains that forces the air upward. As it rises, the air cools and releases its moisture, creating the intense rainfall that defines the South Asian monsoon. Without the Himalaya, the monsoon would be far weaker, and the climates of India, Nepal, Bhutan, and the surrounding regions would look completely different. These towering mountains also shape global wind patterns, gently bending the jet stream and influencing how atmospheric pressure systems form and move across the world. Their presence helps guide storms, influence seasonal changes, and control the timing of rains essential for agriculture. The Himalaya serve as a vast atmospheric engine, turning the collision of continents into weather patterns that sustain entire civilizations. Deep earthquakes occur where slabs bend into the mantle. Most earthquakes happen close to the surface, yet some originate far below in regions where subducting slabs bend and descend into the mantle. These deep earthquakes can occur hundreds of miles beneath our feet, far beyond the depth at which rocks are expected to break in the usual way. Scientists believe that these deep quakes are driven by unusual processes, such as transformations within minerals that release sudden bursts of energy, or the rapid movement of fluids within the slab. As the descending plate is compressed and heated, its minerals rearrange into new forms that may trigger sudden shifts. These quakes travel through the mantle and provide valuable information about the structure of sinking slabs. Because they occur so deep, they rarely cause damage at the surface, yet they offer a rare glimpse into a world of crushing pressure and intense heat. where the behavior of rock is entirely different from that at shallow depths. Some quakes happen hundreds of miles beneath our feet. There are earthquakes so deep that they defy ordinary intuition. These events take place at depths where temperatures and pressures are so extreme that rocks should deform slowly rather than fracture. Yet, seismic instruments record sharp jolts of energy from regions deep within the mantle, sometimes originating nearly 400 meters below the surface. At these depths, minerals transform into denser forms as they are pushed under overwhelming pressure. These changes can release energy in sudden bursts that behave like earthquakes. Some scientists also suggest that fluids trapped within slabs may trigger deep movement as the plate warms and dehydrates. These deep quakes help map the sinking slabs and reveal their shapes as they plunge toward the interior. They are powerful reminders that Earth remains active at depths far beyond human reach, and that the processes shaping our world extend into the hidden interior, where rocks behave in mysterious and unexpected ways. Slow slip events reveal hidden movements along faults. Not all tectonic motion occurs in sudden, violent earthquakes. In some regions, faults move gradually over days, months, or even years, in what scientists call slow slip events. During these episodes, the fault surfaces slide past each other at a pace too gentle to call shaking that humans can feel. Seismic instruments detect faint signals of movement, while GPS stations record small but measurable shifts in the landscape. These slow slips can release as much energy as large earthquakes, yet they do so quietly, offering a peaceful counterpart to sudden seismic ruptures. Sometimes, slow slip events precede major earthquakes, while in other cases, they relieve stress and reduce the likelihood of a large rupture. Studying them helps scientists understand how faults store and release energy, and how different regions of a fault behave under varying conditions. These silent movements reveal a subtle dance beneath the surface that continues long after the last visible earthquake has faded. Invisible tremor waves vibrate continually through Earth, deep within subduction zones. Tiny vibrations ripple through the crust in patterns known as tremor waves. They are too gentle for humans to feel, yet sensitive instruments detect them as continuous humming signals that can last for hours or days. These tremors often occur alongside slow slip events, and may reflect the movement of fluids or the creeping motion of rocks deep within the fault. They do not produce sudden jolts, but instead form a constant background whisper of tectonic activity. Tremor waves help scientists identify the boundaries of subducting slabs and understand how faults behave at depth. Their persistent presence shows that plates rarely rest completely. Instead, they shift and adjust in tiny increments that record the friction, heat, and pressure shaping the subsurface. Tremor waves act as a quiet voice of the deep Earth, carrying information from places too remote and inaccessible for direct observation. Mantle plumes can punch through crust like blue torches. Mantle plumes are powerful columns of rising hot material that originate deep within the mantle. As they ascend, they bring intense heat toward the crust, sometimes melting it enough to create massive volcanic eruptions. When a plume reaches the base of a plate, it can punch through the crust and form large volcanic provinces or long chains of islands. Unlike volcanoes at plate boundaries, plume-driven volcanoes occur even in the middle of plates, where the crust would otherwise remain relatively quiet. The arrival of a plume can create enormous volumes of magma, reshape landscapes, and influence global climate through the release of gases into the atmosphere. Some plumes remain active for millions of years, leaving trails of volcanic activity that track the movement of the plate above. The power of mantle plumes reveals the deep thermal forces at work within the planet, pushing upward with enough energy to reshape continents and oceans from below. Massive flood basalts once reshaped Earth's surface. Throughout Earth's history, there have been rare but astonishing events in which huge volumes of lava poured onto the surface in repeated eruptions that lasted for hundreds of thousands of years. These flood basalts covered vast regions with thick layers of solidified lava, sometimes stacking into plateaus thousands of feet thick. Such eruptions occurred when enormous quantities of magma rose from deep within the mantle, often associated with the arrival of mantle plumes. The Siberian traps and the Dean traps are examples of these immense volcanic provinces. The gases released during these events can alter global climate, influence ocean chemistry, and affect life on a massive scale. Flood basalts reshape landscapes, bury ecosystems, and leave behind rock formations that stretch across hundreds of miles. They stand as reminders that volcanic activity can occur not only in small bursts, but also in world-changing episodes that transformed the surface for millions of years. The Siberian traps erupted for an astonishing length of time. One of the most dramatic volcanic events in Earth's history occurred in the region that is now Siberia, where repeated eruptions built layer upon layer of basalt across a vast territory. These eruptions were not brief moments, but part of a prolonged episode that continued for an extraordinary length of time. The volcanic activity released immense amounts of gas, including carbon dioxide and sulfur-rich compounds, into the atmosphere. These emissions altered climate patterns, warmed the planet, and affected the chemistry of the oceans. Many scientists believe that the environmental changes triggered by the Siberian traps played a role in one of the largest mass extinctions known from the fossil record. The region today contains thick sequences of basalt that reveal the scale of this ancient volcanic event. The Siberian traps demonstrate how deep mental processes can influence both geology and life on a planetary scale. The Deccan traps coincide with a global transformation. In what is now India, another enormous volcanic province formed through repeated eruptions that lay down thick layers of basalt, known as the Deccan traps. These eruptions unfolded during a time of profound planetary change, a period marked by shifting climates and the disappearance of many species. The volcanic activity released vast amounts of gas into the atmosphere, affecting global temperatures and altering the planet's chemical balance. Some scientists believe that the environmental stress triggered by the Deccan eruptions added to the difficulties faced by ecosystems during this turbulent chapter in Earth's history. The timing of these eruptions overlaps with the impact of a large extraterrestrial object, adding complexity to the story of global transformation. The lava flows of the Deccan traps record the scale of volcanic energy unleashed from deep within the mantle. Their presence offers insights into how Earth responds to massive internal and external forces acting simultaneously across the planet. Supervolcanoes are linked to ancient plate interactions. Supervolcanoes are not ordinary volcanic features. They arise from deep-seated processes connected to the slow and powerful interactions of tectonic plates. When plates collide, stretch, or shift over long periods of time, they can create weaknesses in the crust that allow enormous reservoirs of magma to accumulate beneath the surface. Some of these magma chambers grow far larger than those of typical volcanoes, storing vast amounts of molten rock rich in gases. Over immense spans of time, this magma becomes highly pressurized as the heat rises from below and gases concentrate within it. In some cases, the crust above thins or fractures due to old plate boundaries or ancient rifting events, allowing the immense pressure to build without immediate release. When a supervolcano finally erupts, it does so with tremendous force, altering landscapes, affecting global temperatures, and leaving behind calderas many miles across. These extraordinary volcanic systems often sit in regions shaped by long histories of plate movement that created destructural pathways allowing deep magma to gather. Their existence shows how ancient tectonic events can leave behind scars that influence eruptions millions of years after the original plate interactions occurred. Yellowstone sits above a deep-rooted hotspot. Beneath the calm forests and steaming geysers of Yellowstone lies a plume of rising heat that originates deep within the mantle. This hotspot remains fixed in place, while the North American plate drifts slowly across it, leaving a trail of volcanic features that stretch across the continent. Yellowstone itself is only the latest expression of this long-lived plume. The heat from below melts the crust, feeding a vast and evolving magma reservoir that powers the region's famous thermal springs, boiling mud pools, and occasional volcanic activity. Although the surface appears peaceful, the landscape rests on layers of cooled lava, ash, and caldera remnants from ancient eruptions. Scientists study the seismic signals passing through Yellowstone to map the shape of the magma chamber and the plume beneath it. The Yellowstone hotspot illustrates how deep thermal forces can shape the surface far from any plate boundary. It is a reminder that the mantle remains active even beneath regions that seem geologically quiet on the surface. Rift valleys can eventually become vast oceans. When continental plates begin to stretch and pull apart, long rift valleys open across the landscape. These valleys are marked by steep cliffs, volcanic activity, and basins, but may fill with lakes. As the rifting continues, the crust becomes thinner and magma rises to create new crust along the widening fractures. Over millions of years, the valley deepens and may eventually allow seawater to flow in, transforming the rift into a young ocean basin. This is how many of Earth's major oceans began, including the Atlantic, which opened from a similar rift long ago. Rift valleys, such as the East African Rift, show the early stages of this transformation. The spreading forces, volcanic activity, and changing landscapes reveal a young continent beginning to reshape itself. If the rifting continues, the land will split entirely, creating coastlines and new oceanic crust. Rift valleys are gateways to the birth of oceans, offering a glimpse into the slow but profound processes that reshape continents. The Atlantic once looked like today's East African Rift. Before the Atlantic Ocean became the vast expanse we know, it began as a narrow system of rift valleys that resembled the modern East African Rift. Faults opened through a once continuous landmass, creating long depressions bordered by high cliffs and volcanic fields. Sea Eater had not yet entered the rift, and the region would have appeared as a landscape filled with lakes, young volcanoes, and widening valleys. As the continental crust stretched, it eventually thinned enough for magma to rise and produce new oceanic crust. Once this process began, seawater flooded the region, and the rift transformed into a developing ocean basin. Over immense stretches of time, continued spreading widened the basin into the ocean we know today. Studying the East African Rift allows scientists to watch a similar process in real time. It provides a living window into the earliest stages of ocean formation, echoing the distant past when the Atlantic was little more than a cracking seam between drifting continents. Transform faults allow plates to slide sideways. Along transform faults, tectonic plates neither collide nor pull apart. Instead, they slide past each other horizontally in a movement known as strike-slip motion. These boundaries can extend for hundreds of miles and are often marked by straight valleys, offset streams, and linear ridges that show the direction of the sliding motion. Despite their quiet appearance, transform faults store significant stress as two massive blocks of crust grind against one another. When this stress is released, earthquakes occur. Some transform boundaries lie along ocean floors, connecting spreading ridges into continuous networks. Others cut across continents, shaping the landscapes above them. Transform faults play a crucial role in accommodating the motion of plates as they move in different directions. They act as edges that release built-up energy slowly over time or suddenly through seismic jolts. These sideways moving boundaries reveal another dimension of plate tectonics, showing that the Earth's surface shifts in more ways than simple pushing or pulling. The San Andreas Fault is only one of many transform boundaries. The San Andreas Fault is widely known for its seismic activity, yet it is only one example of a transformed boundary among many distributed across the globe. This fault marks the meeting point of the Pacific Plate and the North American Plate, which slide past each other in a slow but persistent motion. The region is threaded with countless smaller faults branching off from the main boundary, each one adding to the system's complex behavior. Similar transform boundaries can be found in Africa, the Middle East, New Zealand, and along mid-ocean ridges. Many of these boundaries produce frequent earthquakes and quietly sculpt the landscapes that surround them. Some lie beneath the ocean, hidden beneath thousands of feet of water. Yet they play an essential role in guiding the movement of plates across the seafloor. The San Andreas is famous because it cuts through populated regions, but the global network of transformed boundaries is far larger, revealing how common sideways plate motion truly is. Continental crust thickens under colliding plates. When continents collide, the crust between them undergoes compression so intense that it thickens dramatically. Rocks stack upon one another, fold into intricate patterns, and may even be thrust upward along large faults. As the crust thickens, it becomes buoyant and rises, forming mountain ranges that can stretch across entire regions. Deep beneath these mountains, rocks are subjected to high pressures and temperatures, transforming into new metamorphic forms. Some rocks may even melt partially, feeding volcanic activity in the collision zone. The thickened crust also affects gravity, groundwater flow, and erosion patterns. Over millions of years, erosion exposes deeper layers, revealing the complex internal structure of the mountain belt. Regions such as the Himalaya and the Alps contain crustal thicknesses far greater than the global average, demonstrating the immense power of continental collisions. The thickening of the crust is one of the clearest indicators of the forces at work when continents converge. Tectonic pressure can warp land without breaking it. Not all deformation caused by tectonic forces results in fractures or faults. In many regions, pressure builds gradually and bends the crust into smooth, sweeping curves known as folds. These folds can extend across miles of rock and may take millions of years to develop. The layers bend because the crust behaves like a solid over short periods of time, yet becomes more flexible when pressure acts slowly across vast spans of time. The result is a landscape shaped not by sudden breaks, but by gentle, persistent warping. These folded structures can appear in mountain belts along continental margins, or in regions where plates compress one another. Their shapes reveal how rocks flowed and adjusted to the pressure without shattering. By studying folds, scientists can reconstruct the history of stress that shaped the land. These graceful curves remind us that the Earth bends long before it breaks, recording its slow adjustments in patterns carved deep into the crust. Rocks can fold into immense curving structures under the right combination of heat, pressure, and time. Rocks that seem rigid and unyielding can fold into elegant arcs that stretch across entire mountain ranges. These folding events occur when tectonic forces compress the crust, squeezing layers of sedimentary or metamorphic rock into looping shapes. Some folds are gentle and broad, while others are tight and intricate, reflecting the intensity of the forces that shape them. These structures can rise into anticlines, where layers arch upward, or sink into sinkiness, where layers bend downward. Over millions of years, erosion can carve through these folds to reveal their internal patterns, creating dramatic cliffs and valleys. Folds record the history of continental collisions, the motion of ancient seas, and the long evolution of mountain belts. They show that rocks are not static, but capable of bending and flowing when the planet presses upon them with slow, persistent force. Some mountain ranges hide entirely buried roots. Beneath many mountain ranges lie deep roots that extend far into the crust, balancing the immense height of the peaks above. These roots form when the crust thickens during continental collisions. The buoyant mass of rock sinks deeper into the mantle, much like the submerged portion of an iceberg beneath the water. Although hidden from sight, these roots play a crucial role in supporting the mountains and stabilizing the range. Over time, changes in temperature, pressure, and erosion can remodel these deep structures. Some roots slowly rise as the mountains erode, bringing ancient rocks to the surface. Others remain buried, preserved as frozen reminders of long-vanished mountain belts. By studying seismic waves, scientists can map these hidden features and discover the full extent of ancient collision zones. Mountain roots reveal that every tall range has a vast, unseen counterpart below, shaped by the same forces that lifted the peaks toward the sky. Plate tectonics is responsible for creating many of Earth's most treasured minerals. The precious and essential materials we depend on are often formed or concentrated through the slow, powerful movement of tectonic plates. As plates collide, pull apart, or glide past one another, they generate heat, pressure, and circulating fluids that carry elements through the crust, quietly shaping the resources that sustain civilizations. These forces create perfect environments for minerals to grow and collect in rich deposits. Gold, copper, zinc, silver, and countless other metals often form in regions shaped by ancient subduction zones or volcanic arcs, where fluids carry dissolved metals through cracks and pores. As these fluids cool, the metals crystallize into veins that can become valuable or deposits. Diamonds are formed under pressures associated with deep continental roots and are brought to the surface through volcanic events linked to plate motions. Even gemstones such as sapphires, rubies, and emeralds owe their origins to metamorphic and igneous conditions created by shifting plates. Without plate tectonics, the crust would remain far more uniform and would lack the concentrated mineral deposits that support modern technology and human civilization. Many ore deposits form at ancient plate boundaries. Some of the richest mineral resources on the planet are found along boundaries where plates once collided or split apart. These ancient zones are preserved in the crust long after the original tectonic activity has ended. During the time when the plates moved, fluids rich in metals circulated through cracks and faults, depositing minerals as they cooled. Over millions of years, additional layers of rock buried these deposits, protecting them until erosion or uplift brought them closer to the surface. Volcanic arcs created during ancient subduction events often contain gold and copper deposits, while rift zones can hold minerals such as lead, zinc, and rare earth elements. Even regions that appear calm today may hide deep geological histories rich in ore-forming processes. The metals that support modern society often originate in these long-forgotten tectonic environments, showing how deeply the Earth's shifting plates influence human life. Earth's magnetic field records plate motion in stripes. As molten rock rises along spreading ridges and cools to form new ocean floor, minerals within the rock align with the Earth's magnetic field. Because the magnetic field has flipped many times throughout history, these minerals capture a record of the field's direction at the moment they solidify. As plates move away from the ridge, they carry these magnetic signatures with them. The result is a symmetrical pattern of magnetic stripes on either side of the ridge, with each stripe reflecting a past magnetic reversal. These patterns allow scientists to determine how fast plates spread, how often the field has flipped, and how ocean basins have evolved through time. The magnetic stripes provide a natural barcode of Earth's geological past, revealing the steady creation of crust and the gradual drift of continents. This discovery was one of the crucial pieces of evidence that confirmed the reality of plate tectonics and transformed our understanding of Earth's history. Seafloor stripes proved that continents move. Before the discovery of magnetic stripes on the seafloor, the idea that continents drifted was controversial. Many scientists were skeptical that entire land masses could move across the Earth's surface. The symmetrical bands of magnetic patterns on either side of the mid-ocean ridges changed everything. These stripes showed that new crust was continuously formed at the ridges and pushed outward in both directions. The discovery provided a clear, measurable record of spreading and proved that continents attached to the plates must be moving as well. The stripes revealed the age of the seafloor, with younger rocks near the ridge and progressively older rocks farther away. This evidence demonstrated that the seafloor was not static, but constantly renewed and shifted by tectonic forces. Together with other clues, such as fossil patterns, matching coastlines and seismic activity, the magnetic stripes provided clear and decisive evidence that continents slowly drift over time. This discovery became a turning point, leading to the acceptance of plate tectonics as geology's unifying theory. The emergence of plate tectonics transformed the entire field, reshaping our understanding of Earth and the forces that continually sculpt its surface. Before plate tectonics, many geological phenomena seemed disconnected. Mountain ranges, earthquakes, volcanoes, and continental shapes were understood only in fragments. When the theory of plate tectonics emerged, it unified all these observations into a single, elegant explanation. It showed that the Earth's lithosphere is divided into moving plates that drift on the softer mantle below. With this understanding, scientists could explain why earthquakes follow clear boundaries, why volcanoes form in arcs, why continents fit together like puzzle pieces, and why rocks of similar age appear on opposite sides of oceans. The theory reshaped the study of Earth, guiding new research in paleontology, climate science, mineral exploration, and planetary evolution. Plate tectonics revealed that the planet is dynamic and alive, with slow but powerful forces that continually renew and reshape its surface. It stands as one of the most important scientific concepts of the modern era, transforming our understanding of Earth from a static world into a living, shifting system. GPS stations track plate movement with stunning precision. Around the globe, thousands of GPS stations quietly observe the movement of tectonic plates. These instruments detect changes in positions so small they would be invisible to the naked eye. Over days, months, and years, the stations record the steady drift of continents, the gradual buildup of strain along faults, and the subtle deformation of landscapes responding to deep forces below. Scientists use this data to create detailed maps of plate motion, revealing which regions are moving fastest, which are locked under stress, and which are slipping slowly. GPS observations have shown that even the most stable-appearing regions experience movement. These precise measurements help predict where seismic hazards may be higher and allow researchers to monitor changes near volcanoes and earthquake zones. The wealth of information gathered by GPS has transformed plate tectonics from a theory based on geological evidence into a real-time observation of Earth's surface in motion. Volcanoes on different plates erupt in distinct styles. The style of a volcanic eruption depends deeply on the tectonic setting in which the volcano forms. Volcanoes above subduction zones often produce explosive eruptions because their magma is rich in dissolved gases and thick in consistency. These volcanoes may create towering ash ponds and powerful pyrolastic flows. In contrast, volcanoes located on spreading ridges or hotspots often produce flowing lava, but spreads out in wide, gentle sheets because the magma is hotter and less viscous. Some volcanoes erupt underwater, forming pillow-shaped lava as it cools instantly upon contact with seawater. Others build tall volcanic islands or produce repeated eruptions that form entire mountain chains. Each tectonic setting influences the chemistry, temperature, and gas content of the magma, shaping the way the volcano behaves. The diversity of volcanic styles reflects the diversity of plate interactions and the deep processes that generate magma in different environments. The shape of coastlines echoes ancient connections. Many modern coastlines reflect the scars of ancient rifting and the remnants of long-vanished connections between continents. When land masses split apart, the jagged edges of the separation can create coastlines that mirror one another across great distances. The famous match between the coasts of South America and Africa is only one example. Other regions, such as the margins of India, Antarctica, and Australia, also contain clues of past arrangements. Subtle indentations, proteries, and curved bays. They all be shaped by the geometry of ancient faults and the stretching that occurred during the breakup of supercontinents. Some coastlines sit along old passive margins, where rifting once opened new oceans. Others mark places where continents were torn into fragments and carried far apart. The shape of a coastline is often more than a natural border. It is a geological memory preserved in rock and geography, hinting at the long journeys continents have taken. Earth's surface would be flat without plate tectonics. If plate tectonics did not exist, Earth would be a very different and surprisingly dull world. The constant motion of plates creates mountains, valleys, volcanoes, islands, and ocean trenches. Without these forces, erosion would slowly wear the surface down until the planet became a mostly uniform, low-lying landscape. There would be no towering peaks like the Himalaya, no deep trenches like the Marana, and far fewer volcanic islands. The continents would have much less variation in climate because mountains play a major role in directing winds and rainfall. The diversity of ecosystems would be dramatically reduced. The Earth's interior heat would remain trapped, with no efficient way to release it. Plate tectonics is responsible for nearly every major landform. It constantly renews the crust, allowing fresh landscapes to rise and old ones to disappear. Without it, the planet would be smoother, quieter, and far less dynamic. Life on Earth may depend on plate-driven recycling. The movement of plates does far more than reshape landscapes. It drives a long-term recycling system that helps regulate the atmosphere, oceans, and climate in ways essential for sustaining life. When volcanoes release gases from the mantle, they replenish the atmosphere with carbon dioxide and other elements necessary for plants and marine organisms. When mountains rise and slowly wear away, their minerals interact with the atmosphere and draw in carbon dioxide, helping to steady Earth's global temperatures. Through subduction, water and carbon-rich rocks are carried deep into the mantle, where part of this material eventually returns to the surface through volcanic activity. This quiet, continuous exchange of elements between Earth's surface and its interior creates a long-term balance, one that helps keep our planet stable, temperate, and habitable. Without plate tectonics, the carbon cycle could stall, oceans could lose vital nutrients, and the planet might become too hot or too cold for complex life. Plate motion may be one of the key reasons Earth remains a living world. Plate tectonics helps regulate carbon through deep time. Earth's carbon cycle is not limited to the atmosphere, oceans, and living organisms. Deep within the crust and mantle, plate tectonics drives a powerful and long-term exchange of carbon, but helps keep the planet's climate stable. When mountains rise through continental collisions, rocks rich in minerals that react with carbon dioxide are exposed to rain and air. Over millions of years, these reactions remove carbon dioxide from the atmosphere and store it in carbonate rocks. At the same time, subduction carries carbon-rich sediments into the mantle, where some of this carbon is stored for immense stretches of time. Volcanoes later release portions of it back into the atmosphere, returning carbon that would otherwise be locked away forever. This balance between storage and release prevents carbon dioxide levels from rising or falling too dramatically across geological ages. Without the constant recycling driven by plate motion, Earth's climate would drift into extremes that could endanger life. The interplay between the surface and the deep interior reveals a planet that regulates itself slowly and steadily through its own tectonic heartbeat. Without plate motion, Earth might resemble a lifeless world. The slow drifting of continents and the recycling of crust may seem unrelated to life, yet they are essential for maintaining the conditions that allow organisms to thrive. Without plate motion, the deep carbon cycle would stagnate. Volcanoes would become rare, shutting down the natural release of gases that replenish the atmosphere. Weathering of mountains would slow, reducing the drawdown of carbon dioxide that keeps global temperatures in balance. Oceans would lack many of the minerals and nutrients delivered by volcanic eruptions, and the erosion of rising mountain ranges. Over time, the atmosphere could become too hot, too cold, or too depleted to sustain life as we know it. Planets without plate tectonics often show signs of climate instability or atmospheric loss. By continually renewing the crust and recycling essential elements, plate motion helps maintain a dynamic equilibrium that supports complex ecosystems. Earth's living richness is closely tied to the restless movement beneath its surface. Venus may lack plate tectonics and shows the consequences. Venus is often called Earth's twin because of its similar size and overall composition. Yet its surface tells a very different story. Unlike Earth, Venus appears to lack active plate tectonics. Instead of a mosaic of moving plates, its crust seems to behave as a single, rigid shell. Without subduction zones to recycle heat and material, the planet's interior may trap energy until it is released in catastrophic volcanic resurfacing events. Much of Venus is covered by lava plains that suggest large-scale eruptions reshape the surface in relatively recent geological times. The atmosphere of Venus is dominated by thick clouds of carbon dioxide, creating temperatures hot enough to melt lead. Without the cooling, recycling, and balancing effects of plate motion, carbon may have accumulated unchecked in the atmosphere. Studying Venus helps scientists understand the importance of tectonics in regulating planetary environments. It offers a glimpse of how a world similar to Earth can become hostile when deep geological processes operate differently. Mars displays clues to an ancient tectonic past. The surface of Mars appears quiet today, with no clear signs of active plate tectonics. However, its landscapes contain hints that the planet may once have experienced tectonic processes during earlier stages of its history. Large volcanic structures, such as Olympus Mons, rise to heights far greater than anything on Earth, suggesting that the crust remained stationary over long-lived volcanic hotspots. Rift valleys, like Thas Marinaries, stretch for thousands of miles and resemble features formed by crustal stretching. Magnetic stripes preserved in the crust of Mars hint that its magnetic field may once have reversed, a behavior associated with tectonic cycling on Earth. Although Mars no longer shows evidence of active plates, these ancient signatures suggest that the planet once possessed internal heat and forces capable of reshaping the surface. Over time, Mars cooled and its crust thickened, shutting down tectonic motion. The remnants of its tectonic youth reveal how planetary interiors evolve and how their geological stories unfold. Some exoplanets may even have their own versions of plate movement. As astronomers continue discovering planets around distant stars, they are beginning to recognize worlds that could host tectonic activity of their own. The motion of plates depends on a delicate balance: internal heat, the composition of the crust, and the presence of water or other materials that allow the surface to bend and shift over time. Some rocky exoplanets may be large enough and warm enough to sustain convection within their mantles, creating forces capable of driving plate motion. Others may have surfaces that deform in ways unlike Earth, producing unique forms of tectonics shaped by different compositions or temperatures. Observations of their atmospheres may reveal gases associated with volcanic activity, while studies of their densities and thermal properties hint at dynamic interiors. If tectonics is common among rocky planets, then many worlds across the galaxy could maintain climates and environments capable of supporting life. These distant planets may demonstrate that Earth's geological vigor is not unique. Tectonic activity can create habitable conditions on other worlds. On any planet, life depends on a stable climate, a supply of nutrients, and the recycling of essential elements. Tectonic activity can provide all three. When plates move, they expose fresh rocks to weathering, releasing minerals into oceans or lakes. Volcanic eruptions release gases that help maintain an atmosphere capable of trapping heat. The recycling of crust moves carbon and water between the surface and the interior, preventing the atmosphere from becoming too thick or too thin. On worlds with enough internal heat and the flexible crust, tectonics could help maintain habitable conditions for billions of years. Even moons orbiting giant planets might experience tectonic-like processes driven by tidal forces rather than internal heat alone. In such places, the bending and stretching of the crust could generate heat that melts ice and maintains subsurface oceans. Tectonics, in all its forms, is one of the most powerful engines for creating environments where life could flourish. Earthquake lights might be linked to tectonic stresses. Across history, people have reported mysterious glows, flashes, or faint illuminations in the sky before or during earthquakes. These rare phenomena, known as earthquake lights, remain one of the most intriguing puzzles in geology. Some scientists propose that intense tectonic stresses deform rocks in ways that release charged particles into the air. These particles may ionize the surrounding atmosphere, creating faint glows or flashes of light. Others suggest that friction along faults generates electrical fields strong enough to produce visible effects. Although the exact cause remains uncertain, these lights are often reported near major fault zones or during strong seismic events. Modern instruments occasionally detect unusual electromagnetic signals before earthquakes, hinting that the rocks under stress may behave in unexpected ways. Earthquake lights remind us that tectonic processes can influence not only the ground beneath our feet, but also the air above, producing phenomena that blend geology with atmospheric physics. Strange rocks called ophiolites reveal ancient ocean floors. In some mountainous regions, geologists find unusual rock sequences that once formed the crust of ancient oceans. These rocks, known as ophiolites, include layers of deep-sea sediments, oceanic crust, and upper mantle material that were thrust upward during ancient collisions between plates. Ophiolites provide a rare chance to study parts of the ocean floor without needing to drill deep beneath the sea. Their minerals record the chemistry of ancient spreading ridges, the movement of hydrothermal fluids, and the structure of the mantle beneath old oceans. They reveal how oceanic plates formed, aged, and eventually met their end in subduction zones. These rocks are often found in mountain belts created by continental collisions, where slices of oceanic crust were scraped off and preserved on land. Oolites allow scientists to reconstruct the vanished oceans that once separated continents and to understand how the seafloor evolves through time. Some continents still carry hidden pieces of long-lost plates. Not every tectonic plate from Earth's past remains intact today. Many were completely drawn down and consumed through subduction. Yet traces of them endure, locked within continents as small fragments of ancient crust. These remnants often appear as unusual geological terrains, standing apart from the surrounding rocks and hinting at worlds that vanished long ago. They often contain fossilized ocean floor, volcanic arcs, or island remnants carried long distances before becoming welded to a continent. By studying these fragments, scientists identify the paths of lost plates and the oceans that once existed between landmasses. These preserved pieces reveal the complexity of Earth's tectonic history, showing that continents grew through the gradual addition of pieces torn from other regions. Each fragment carries a record of environments that no longer exist, including coral reefs, volcanic islands, and deep ocean sediments. They are geological time travelers, offering glimpses of landscapes erased from the surface long ago. Earth's restless crust continues to shape its future. Even now, with continents appearing familiar and oceans seemingly permanent, the surface of Earth remains in motion. Plates continue to drift, collide, open rifts, and build mountains. Volcanoes erupt along boundaries and hotspots, seeding new land with minerals and gases. Earthquakes shift coastlines and reshape valleys in moments, revealing the tension stored over years. The planet is not finished evolving. New oceans will form where continents stretch, and existing oceans will close where plates converge. Mountains will rise in some regions and erode in others. Climate patterns will shift, as continents wander toward new latitudes. The slow but unstoppable movement of Earth's crust ensures that the planet of the distant future will look very different from the world we know. Plate tectonics continues to write the story of Earth, one slow-motion chapter at a time. As we reach the quiet end of our journey, let the thoughts of shifting continents and drifting oceans settle softly in your mind. The world beneath your feet is never still, yet its movements are so patient and so vast that they whisper rather than shout. In that slow rhythm, there is a kind of comfort, a reminder that change can be gentle, steady, and deeply natural. Plate tectonics tells the story of a planet that carries its history within every mountain and every valley. It shows us that even the hardest stone flows when time grows deep enough. If you enjoyed this calm exploration, I invite you to like, subscribe, or share a peaceful thought below. It helps others find their way here too, one sleepy soul at a time. But for now, let your breath soften. Allow your body to grow heavy, and let the drifting world cradle your thoughts. Sleep well, and good night.